In the early morning hours of August 6, 1945, a single American aircraft released a single bomb over the Japanese city of Hiroshima. In less than a second, a 4-square-mile section of a modern urban center ceased to exist. The thermal pulse reached temperatures hotter than the surface of the sun. The overpressure wave demolished reinforced concrete structures. The blast radius killed approximately 70,000 people before the fires even began to spread. Joseph Stalin received the intelligence report within hours. The Soviet leader understood with absolute clarity what this event meant. The Americans now possessed a weapon that could erase a city from the map with a single delivery vehicle. More critically, Stalin understood that the primary target of any future American nuclear strike would not be a Japanese industrial port. It would be Moscow. It would be the Kremlin. It would be the command structure of the Soviet state itself. The fundamental problem facing the Soviet leadership was not ideological. It was architectural. The headquarters of the most powerful military force on the Eurasian continent sat in the center of a flat, open city. There was no mountain range to shield it. There was no river canyon to deflect the blast wave. There was no natural feature on the surface of the Earth that could protect the Soviet government from a thermonuclear weapon descending at terminal velocity from 80,000 feet. Stalin's answer was not to move the government. His answer was to bury it. The mandate that emerged from the Kremlin in the years following Hiroshima was unprecedented in the history of human construction. The Soviet leadership ordered the design and excavation of a complete parallel infrastructure beneath the capital. Not a simple bunker, not a reinforced shelter, a functioning underground system capable of absorbing a direct nuclear strike, maintaining command and control of the Soviet military apparatus, and sustaining the lives of thousands of people for months or years, without any connection to the surface world above them. What the engineers of the Soviet Ministry of Internal Affairs and the specialized construction bureaus would build beneath Moscow over the following 4 decades would become the most classified construction project in the history of the Cold War. And for nearly 40 years, the Western intelligence community would know it existed, suspect its scale, and have absolutely no reliable way to measure the depth or the true purpose of what lay beneath the streets. If the engineering and the tradecraft behind these hidden architectures of the Cold War fascinate you, subscribe to the channel. We reconstruct these declassified programs in precise technical detail, going beyond the surface narrative to examine the mechanics that actually shaped the 20th century. The first question the Soviet engineers faced was purely geological. Moscow sits on a thick sequence of sedimentary deposits, layers of clay, sand, limestone, and waterlogged alluvial material that overlie the ancient Precambrian basement rock hundreds of meters below the surface. This geology is fundamentally hostile to deep excavation. As you drill down through the clay and sand layers beneath the city, you encounter increasingly high groundwater pressures. The water table beneath central Moscow is not a stable, manageable system. It is a complex, interconnected network of aquifers under significant hydrostatic pressure. If you breach those layers with a conventional excavation, the groundwater does not seep in gradually. It floods in catastrophically, collapsing the excavation walls and drowning the machinery. The Soviets already possessed one of the most advanced deep tunneling programs in the world. The construction of the Moscow metro, begun under Stalin's personal direction in the 1930s, had forced Soviet engineers to develop specialized techniques for managing deep excavations through waterlogged geology. They had pioneered the use of compressed air caissons and ground freezing techniques, pumping liquid nitrogen into the earth to create a temporary wall of frozen soil around the excavation, allowing workers to drill through the frozen barrier before the ice thawed. These techniques were dangerous, expensive, and required extraordinary logistical coordination, but they worked. The Soviet leadership looked at this existing tunneling expertise and recognized that the same technical capability that had built a public transit system could be scaled, classified, and redirected to an entirely different purpose. What emerged from the planning bureaus in the late 1940s and continued to expand for the next 4 decades was a layered underground system operating at multiple depths beneath the city. The shallowest layer, operating at approximately 50 to 65 meters below the surface, housed the initial network of reinforced command facilities and transit corridors constructed in the immediate post-war period. But as Soviet thermonuclear weapons became increasingly powerful through the 1950s and 1960s, and as American delivery systems became more accurate, the engineers were forced to go deeper, much deeper. The critical technical threshold was determined by Soviet weapons designers themselves. A modern thermonuclear warhead detonating at optimum burst height above Moscow would generate a ground overpressure sufficient to collapse any reinforced structure within a certain radius. At 50 meters of depth, with the geological dampening provided by the clay and limestone layers, a facility had a calculable probability of surviving the initial blast. But the electromagnetic pulse generated by a high-altitude detonation could penetrate to that depth and destroy unshielded electronics. The thermal radiation would superheat the surface layers, and the sustained ground shock from multiple warheads could propagate downward and compromise structural integrity. To achieve genuine survivability against a full American first strike, the Soviet engineers calculated that key command facilities needed to be positioned at depths between 150 and 200 meters below the surface. At those depths, the combination of geological dampening, reinforced concrete construction, and shock-mounted internal structures could provide the survival probability that Soviet military planners required. Excavating at 200 meters beneath a densely populated urban center, in secret, without disrupting the surface infrastructure above, was an engineering challenge that had no historical precedent. The solution required the expansion of the existing metro tunneling infrastructure as a cover operation. The public Moscow metro system provided the perfect logistical mask. Large volumes of excavated earth, specialized tunneling equipment moving through the city, and the roar of drilling machinery could all be attributed to the constant expansion and maintenance of the existing transit network. The civilians living and working on the surface had long since learned not to ask questions about what the construction crews beneath their feet were actually building. The projects that Western analysts would eventually designate by multiple classified code names, and that Soviet insiders referred to variously as the D6 line or Metro 2, was not a single facility. It was an arterial network. Beginning beneath the Kremlin complex itself and extending outward along several distinct corridors, the underground system connected the most critical nodes of Soviet power. The Ministry of Defense headquarters on Arbatskaya Square was connected to the General Staff facilities. The command bunker beneath the Ramenki district in the southwestern suburbs of the city was linked to the central arterial. The heavily classified facility beneath the Vnukovo II government airport was tied into the network, providing an emergency evacuation corridor for senior leadership that bypassed the surface road system entirely. The transit corridors connecting these nodes were not narrow maintenance passages. Declassified accounts from Soviet-era engineers and the testimonies of multiple defectors described mainline tunnels wide enough to accommodate a specialized high-speed rail system. The trains running through the D6 network were reportedly similar in gauge to the public metro carriages above, but they were not designed to carry commuters. They were designed to move the Soviet government from the Kremlin to a survivable command facility within minutes of a launch warning. Consider what this means operationally. The Soviet early warning system, monitoring American intercontinental ballistic missile launches from silos in the American Midwest, provided a flight time window of approximately 25 to 30 minutes before warheads reached Moscow. In that narrow window, the Soviet leadership had to receive the warning, authenticate it, make the decision to initiate a retaliatory strike, and physically evacuate to a protected command position from which they could execute and sustain that retaliation. 25 minutes. On a surface road network in a city of 8 million people in the chaos following an emergency broadcast, that timeline was essentially impossible. But 200 meters below the surface, on a rail system with no civilian traffic, no intersections, and no weather, the window was entirely achievable. The command facility at Ramenki became one of the most intensely analyzed targets in the CIA's order of battle assessments for the Soviet Union. What the American intelligence community eventually pieced together from defector reports, satellite imagery, and signals intelligence suggested that the Ramenki complex was not a bunker in the conventional sense. A bunker implies a hardened room. What existed at Ramenki appeared to be an entire self-contained subterranean city. Put yourself in the position of an American imagery analyst working at the National Photographic Interpretation Center in Washington in the early 1980s. Your job is to assess the construction signatures of Soviet strategic facilities using overhead reconnaissance from the KH-11 keyhole satellite. When you examine the area surrounding the Remenki district in the southwestern quadrant of Moscow, you see something that is profoundly difficult to interpret. There are no large above-ground structures. There's no visible construction footprint consistent with a major military installation. But there are a series of anomalies. Ventilation shafts disguised as electrical transformer stations, heavily reinforced access points built to resemble ordinary maintenance facilities, periodic ground subsidence patterns in the surrounding streets, consistent with large-scale underground excavation, and an electrical infrastructure serving this district that draws significantly more power than the residential and commercial buildings above ground would require. The signature is invisible in the conventional sense, but it is not absent. The physics of hiding a massive underground installation are inherently problematic. You can conceal the physical construction activity. You can disguise the access points. But you cannot eliminate the thermodynamic and electrical signatures of a large underground facility drawing massive amounts of power, circulating enormous volumes of conditioned air, and operating complex mechanical systems. The thermal signature was particularly revealing. In cold Moscow winters, the ground temperature above a large underground installation is detectably warmer than the surrounding earth. The heat, generated by the ventilation systems, the electrical equipment, and the human occupation of a large underground facility slowly conducts upward through the geological layers above it. When American infrared sensors on reconnaissance satellites scanned the Remenki district, the thermal anomaly was consistent with a facility of significant scale operating continuously beneath the surface. What the American analysts estimated, and what subsequent defector accounts broadly corroborated, was a facility designed to house between 10 and 15,000 people. Not soldiers, not just military commanders. The population of the Remenki underground city reportedly included not only senior military and political leadership, but the administrative, technical, and support personnel required to actually run a functioning government in the aftermath of a nuclear exchange. Communications technicians, nuclear weapons specialists, strategic planning staff, the people necessary to give meaning to the word continuity. The engineering required to sustain that population at 150 to 200 meters below the surface for months or years without surface resupply represents a staggering logistical achievement. The air supply system had to be entirely independent of the surface atmosphere. Following a nuclear exchange, the surface air would be contaminated with radioactive fallout, thermal particulates, and chemical products of combustion from thousands of simultaneous fires. The underground facility needed its own filtered air supply, not just basic filtration, but a multi-stage system capable of removing radioactive particulates, chemical agents, and biological contaminants. The air circulation required enormous mechanical fans and filter banks, each of which generated its own acoustic and electrical signature. The water supply presented an equally complex challenge. The geological layers beneath Moscow contained naturally occurring aquifer systems, and the Soviet engineers tapped these directly, sinking specialized deep wells into the aquifer formations below the facility level. The water was then processed through filtration and chemical treatment systems to ensure it was safe for consumption regardless of any surface contamination. The capacity of these water storage systems was reportedly sufficient for years of operation at full occupancy. Food storage presented its own engineering paradox. A facility designed to house 15,000 people for a multi-year period requires an extraordinary quantity of preserved food. The caloric requirement alone, sustained over a 2-year isolation period, runs into the tens of millions of daily calories. The storage volume this demands is immense, and that volume has to be maintained at controlled temperatures, inspected, rotated, and managed continuously. Declassified Soviet-era procurement records that emerged in the 1990s revealed unusual procurement patterns for specific categories of preserved foodstuffs and military rations that significantly exceeded the known requirements of the surface-based Soviet military. Some of this surplus was being pre-positioned somewhere. But the most critical engineering requirement, the one that overrode every other technical consideration, was command and control. An underground facility capable of housing the Soviet government is operationally worthless if it cannot communicate with the strategic forces it is supposed to command. The specific challenge of underground communications during and after nuclear war is one of the most difficult problems in military engineering. The electromagnetic pulse generated by a high-altitude nuclear detonation is the primary threat. A single warhead detonated at 300 kilometers above the center of the continental United States would generate an EMP that would disable unshielded electronic equipment across the entire country. Surface-based radio communications would be rendered instantly useless. The underground facility needed communication systems that could survive the EMP, penetrate the geological layers above, and reach the strategic forces. The nuclear submarines, the mobile missile launchers, the long-range bomber crews, wherever they were operating. The Soviet solution was the extremely low-frequency radio system. LF signals, operating at frequencies between 3 and 30 hertz, have a remarkable physical property. They can penetrate seawater to depths of hundreds of meters, and they can propagate through the geological layers of the Earth itself with significantly less attenuation than higher frequency signals. The Soviet ELF transmitter network, designated ZEVs and located on the Kola Peninsula, was capable of reaching submerged submarines anywhere in the world's oceans. But more critically for the underground city concept, ELF signals could penetrate the layers of clay and limestone above a deep facility and be received by antennas embedded within the underground structure itself. The facility could receive launch authentication codes even while completely buried. For outbound communications, transmitting the launch orders to the strategic forces, the underground complex was connected to hardened landline networks and to specialized antenna systems buried at shallower depths, below the contaminated surface but above the main facility, designed to survive the initial blast overpressure and allow communication to resume in the minutes following a nuclear strike. The full scope of this underground network only began to emerge in the Western intelligence community's analysis during the 1980s, and what they found deepened an already profound strategic concern. The CIA and the Defense Intelligence Agency had been tracking the construction signatures of Soviet strategic facilities for decades, but the sheer scale of the Moscow underground system defied their initial assessments. The problem was not locating individual facilities. It was comprehending the interconnected scope of what had been built. Individual anomalies, a suspicious ventilation structure here, an unusual electrical draw there, could be explained away as routine infrastructure. But when analysts began to overlay the full data set of thermal signatures, electrical anomalies, construction signatures, acoustic signals from ground-penetrating radar, and the accumulated body of defector testimony, the picture that emerged was of a system far larger than any single Cold War facility. And the Moscow underground network was not the only element of the Soviet government continuity program. In the Ural Mountains, approximately 1,400 kilometers east of Moscow, American satellite reconnaissance had been monitoring a massive construction project at a location designated Yamantau Mountain since the 1970s. The scale of the excavation activity was extraordinary. The spoil heaps, thus the mountains of excavated rock deposited outside the tunnel entrances, were large enough to be visible from low Earth orbit. The railway lines serving the construction site carried an abnormal volume of specialized equipment and materials. The electrical infrastructure being installed was orders of magnitude greater than any civilian mining or industrial project would require. When American officials raised the Yamantau mountain construction directly with their Russian counterparts during the arms reduction negotiations of the early 1990s, the Russian representatives offered a series of explanations that changed over successive meetings. It was a mining project. It was a food storage facility. It was a government emergency management center. The explanations were not internally consistent, and each successive answer contradicted elements of the previous one. What the accumulated satellite intelligence and the emerging pattern of defector testimony suggested to American analysts was a second complete underground command city, not a backup for Moscow, A separate parallel continuity node positioned far enough from the capital that a coordinated American first strike targeting Moscow could not simultaneously neutralize both locations. 2 underground cities, 2 independent command networks, 2 survivable governments. The doctrine of mutually assured destruction rests on a specific assumption. It assumes that a first strike powerful enough to destroy an adversary's cities will also destroy the adversary's ability to retaliate. If the leadership is dead, if the command structure is vaporized, if the communications networks are severed, then the strategic forces have no one to authorize their launch. Mad holds. But a buried government in a Ural mountain, alive in communication with strategic forces, with launch authority fully intact, fundamentally alters the strategic calculus. It does not make nuclear war more likely. It makes the outcome of a nuclear war less certain. And in the mathematics of deterrence, uncertainty is the most dangerous variable of all. Put yourself in the position of an American strategic planner in 1984, being briefed on the full scope of what the imagery analysts and the CIA's Soviet Operations Division had assembled. You are looking at evidence suggesting that the Soviet Union spent decades and an extraordinary quantity of its national industrial output constructing a system designed specifically to survive an American nuclear strike and continue functioning. Your entire deterrence posture is premised on the assumption that a first strike would be mutually suicidal. You are now looking at evidence that the Soviets spent 40 years engineering their way out of that mutual suicide pact. The American response drove a significant escalation in the technical sophistication of penetrating warhead development through the 1980s. If the target was no longer a surface city, but a facility buried at 200 meters beneath 150 meters of reinforced concrete and geological overburden, then existing American warhead designs were inadequate. A warhead optimized for maximum overpressure at surface burst would waste most of its energy pushing air. What was needed was a weapon that could penetrate the geological layers before detonating, a nuclear earth penetrator, a weapon that would deliver its yield directly into the rock surrounding the facility. The engineering requirements for a nuclear earth penetrating weapon are staggering. The warhead casing has to withstand the deceleration forces of driving through solid rock at terminal velocity, forces reaching tens of thousands of Gs, without shattering before it reaches detonation depth. The fusing system has to function reliably after that same deceleration. The nuclear primary has to maintain its precise geometric configuration through the impact. These are engineering challenges at the absolute edge of materials, science, and weapons physics. The existence of the Soviet underground city network directly drove American weapons development in ways that remained classified for decades. The collapse of the Soviet Union on December 25, 1991, did not close the Moscow underground. It orphaned it. The newly formed Russian Federation inherited the entire network, its maintenance requirements, its operational staff, and the extraordinary ongoing cost of keeping it functional. But the economic context that followed the Soviet collapse was catastrophic. The funding simply evaporated. Throughout the 1990s, Russian investigative journalists and independent researchers began to probe the edges of what lay beneath Moscow. The journalist Vadim Mikhailov published detailed accounts of the Metro 2 network based on interviews with former construction workers and operational staff. Researchers documented the ventilation structures and access points visible in the Remenki district. Former KGB officers and Soviet-era government officials, freed by the collapse of the secrecy apparatus, began to confirm the outlines of what American intelligence had been inferring from satellite imagery for decades. What emerged from these testimonies confirmed the broad parameters of the American assessment while revealing details that overhead imagery could never have captured. The underground corridors were not bare concrete passages. They were finished, climate-controlled, and equipped to the standards of a functioning government facility. The command center areas featured operational consoles, communications equipment, and the administrative infrastructure of a working headquarters. The residential areas designated for senior officials were not Spartan military accommodations. They were furnished to a standard commensurate with the rank of the people expected to occupy them. The facility was not designed to feel like a wartime emergency shelter. It was designed to feel like a place where the Soviet government could function, could continue to govern, continue to direct military operations, continue to exist as a legitimate political authority. Indefinitely. The dining facilities were stocked. The communication systems were wired. The air filtration was running. The water was flowing from the deep aquifer wells. And through most of the 1990s, in a nation that could not pay its surface military a consistent wage, the maintenance crews responsible for keeping the underground city operational continued to report for work. The Russian Federation's official position on the Moscow underground network has never been one of acknowledgement. Statements from Russian government spokesmen have ranged from outright denial to deliberate ambiguity. The Russian government does not confirm that Metro 2 exists. It does not confirm the Remenki facility. It does not explain the Yamantau mountain construction. This strategic ambiguity is itself a calculated posture. The value of a survivable command facility depends partly on the adversary's uncertainty about its true capabilities. But the engineering signatures do not lie. The thermal anomalies are still present. The electrical infrastructure is still drawing power. The ventilation systems are still exhausting conditioned air through their disguised surface outlets in the Remenki district. The physics of operating a large underground facility cannot be fully concealed regardless of how effective the surface camouflage is. The defense analysts and strategic planners who have spent careers examining this question continue to debate its fundamental implications. At its most basic level, the Moscow Underground is one of the most extraordinary construction achievements in human history. The sheer volume of material excavated, the depth of the tunneling, the complexity of the mechanical and electrical systems installed, the logistical challenge of constructing all of it in complete secrecy beneath one of the world's largest cities. These are engineering accomplishments that have no genuine parallel. But the strategic dimension is where the debate becomes genuinely difficult. Critics argue that the underground city program represented a catastrophic misallocation of Soviet resources. The billions of rubles poured into subterranean construction, into specialized tunneling equipment, into the maintenance of a parallel infrastructure operating beneath the surface of Moscow for 4 decades, were resources diverted from agriculture, from consumer manufacturing, from the industrial sectors of the Soviet economy that were visibly collapsing under the weight of their own contradictions. The underground city did not cause the Soviet collapse, but it was a symptom of the same systemic disease, an economy that systematically prioritized military survivability over civilian productivity until the civilian economy could no longer sustain the military apparatus riding on top of it. Defenders of the program offer a different analysis entirely. The underground city was not a luxury. It was the foundational requirement of the Soviet deterrence posture. A nuclear arsenal is strategically meaningful only if the authority to authorize its use survives a first strike. Without a survivable command and control infrastructure, the entire Soviet nuclear deterrent was a single point of failure system. One coordinated American first strike targeting the Kremlin and the Ministry of Defense headquarters could, in theory, decapitate the Soviet military command before a single retaliatory missile was authorized. The underground city was the engineering solution to that vulnerability. It was what made Soviet deterrence credible. The deepest irony embedded in the history of the Moscow underground may be this. The system was built to preserve Soviet power through a nuclear war. It was never used for that purpose. The Soviet Union did not end with a thermonuclear exchange. It ended with an economic failure so complete that the government simply dissolved. The underground city, built to house the Soviet leadership through the apocalypse, sat fully operational beneath a city whose government had ceased to exist above it. Today, the network almost certainly remains partially operational in some form under Russian Federation maintenance. The Russian government's continued strategic ambiguity on the subject suggests that whatever functions the underground infrastructure currently serves, those functions are still considered sensitive enough to protect. What the American satellites found beneath Moscow was not simply a bunker. It was the physical expression of an existential fear, the fear that a single morning's worth of thermonuclear weapons could end not just a city, but an entire civilization, and that the only answer to that fear was to put the civilization underground and hope the earth was deep enough. The engineers of the Soviet Ministry of Internal Affairs and the specialized construction bureaus who spent their careers drilling through waterlogged clay 200 meters beneath one of the world's great cities were not building a monument. They were building a hedge against annihilation. Whether that hedge was strategically sound, economically rational, or ultimately futile is a question that historians and defense analysts will continue to argue. What is not arguable is the scale of what they built